In the last class, we have discussed some of the ARM instructions. We shall continue with this instruction set of ARM processors and look at the different modes in which ARM architecture can be enhanced, and corresponding to that, how the instruction set changes. We shall first look at load store instructions. Now, ARM is an example of RISC architecture. So basically, memory access is through load and store. And these load store instructions are therefore for data transfer between memory and processor registers. There are three basic types of load store instructions: single register transfer, multiple register transfer, and swap. In fact, multiple register transfer in case of ARM is a significant departure from classical RISC model or RISC instruction sets. The single register transfer supports signed and unsigned 32-bit transfer, half-word transfer, as well as byte transfer. Let's look at single transfer instructions. These load and store instructions are particularly for transferring data at a boundary alignment. What do we mean by boundary alignment? It means that the data is expected to be aligned at the correct memory address. So, when we load or store a word, the address should be at the 32-bit boundary. When we load or store a half word, it should be at the 16-bit boundary. In fact, these load store instructions support a variety of addressing modes. The simplest addressing mode is register indirect. Here, the memory address is specified in a register. A variation of these will be found in this case, where I have specified an immediate mode offset. This offset is added to the base register to get the memory address. We can even have register operations specified. In this case, I have specified a second register and I have given a minus sign here. It means that there would be an arithmetic operation performed between the content of R1 and R2 for obtaining the memory address. This is true for store instructions as well. There are more addressing modes. One of them is scaled addressing mode. Now, I hope you remember that there is a barrel shifter in the data path of ARM. In scaled addressing mode, the barrel shifter is used for calculation of address. So address is calculated using the base address register and a barrel shift operation. The same set of operations that we had discussed in the context of data processing instructions are applicable here also. Then we have pre and post indexing. This is also a very interesting scheme of addressing memory locations. The two distinct modes are pre-index with write back and post-index. The normal mode that we have seen so far is typical pre-index addressing mode. When we have pre-index with write back, the interesting thing is that when we calculate this address of the memory location, what we have done? We have added the offset, immediate mode offset, with the content of R1. And then what we do? We update the address base register with the new address. Now, why it is a pre-index? Because when we fetch the data, we use the address of R1 plus 4, okay, R1 plus 4, in this case 4 is an immediate value, and then this R1 plus 4 value is loaded onto R1. In contrast to this, we can look at post index. That means we use R1 for referring to the memory, and after we have accessed the memory, we modify R1 and load the modified value of R1 back to R1. So, this is post indexing. So, the pre-index means that this offset is added to the base for accessing memory. In post index, the base value is used for accessing memory, and then base value is added with the offset, and this new value is stored back to R1. So, if I again use this instruction in a loop, then in that case the modified R1 value would be used for accessing next memory location. Let us take an example to understand it better. Here I am illustrating a case of pre-indexing with write back. So, we have got R0 as the target register, and if you look here, what we are telling is that we have got this memory location. Let us say this memory location is has got some value, and then this memory location has got some other value. Now, this register R1, which is my base, is initially loaded with 9 0 0 0. Okay. Now, after I execute the instruction, what happens? My R0 is loaded with content of this memory location, because I have added 4 to R1 to access the memory location. So, my R0 is now loaded with this memory location, and then R1 content is also changed. R1 is content is changed to 9004. This is the basic operations. That means, what you can find out that in case of pre-indexing, the content of two registers, in this case since I am using a load instruction, gets modified, the base register as well as that of the target register. Next, we have got multiple register transfers. In this case, we transfer contents of multiple registers to the memory, or content of multiple memory locations to multiple registers using a single instruction. Obviously, this provides an efficient way of moving blocks of data between memory and the set of registers. And since I am using this multiple byte transfer or word transfer in a single instruction, what happens is that this instruction cannot be interrupted under normal circumstances. So, these instructions may increase interrupt latency. That means, if there is an interrupt pending, that interrupt can only be serviced if and only if I have completed transfer of all these transfers, completed all these transfers from memory or register bank. So, what is the mnemonic used for this multiple byte load store? In this case, I use LDM or HDM, and the base register Rn determines the source or destination address depending on the instruction, whether it is a load instruction or whether it is a store instruction. Now, there are also a number of addressing modes which are supported here. So, I have listed these addressing modes we can have increment after, we can have increment before, we can have decrement after, we can have decrement before. Now, what happens in this case? If you look at the other columns, we have illustrated these operations. The start address, when I am using a addressing mode IA, so what I shall have? I shall have now the instruction LDM IA Rn, and I have got the set of registers. This Rn is the base address is stored in this Rn register, and what I am trying to transfer? I am trying to transfer the content of registers R1, R2, R3. So, the start address is Rn, the end address is this. Why I am having this value? Because I am transferring what? The content of these registers to memory. Since I am transferring content of registers to the memory, so what I shall have? This address has to be incremented, and they have to be incremented by 4. If there are n register content is to be transferred, then it has to be multiplied by 4, because ARM has got byte addressing, because each byte has got a unique address, and I am subtracting minus 4 because it is an increment after. So, final value of Rn is this. Similarly, when I have got an increment before, the start address is Rn plus 4. So, base address is added with the offset 4, and then what we get? The first register value is transferred. Here the end address would become Rn plus 4 into n, okay, and my Rn here also, that is the final value of Rn, will be Rn plus 4 into n. Similarly, I can have decrement after and the decrement before modes. In this case, instead of increment, I have got decrement as the basic operation. So, what we have therefore seen is that using a single instruction, by specifying the base register and by specifying in this case the set of registers here, I can load. Here what is happening? This is a load instruction. So, what I shall be doing? These memory locations pointed to by the base will be loaded onto these registers. If instead of that, if I got store, I shall be storing the content of the registers onto the corresponding memory locations, and the addresses of the memory locations will be given by the content of Rn. Now, these multiple register instructions in various ways facilitate stack processing. Now, what is a stack? Stack is implemented as a linear data structure which grows up or down. So, I can have growing up stack or I can have a growing down or a descending stack. And stack pointer register hold the address of the current top of the stack. Now, how shall I use these different addressing modes that I have discussed in the context of stack? Do we really need special push and pop instructions? Strictly speaking, I do not need. Why? Because I have got a symmetric organization. With any of the registers as base registers, I can use these addressing modes. If I am using these addressing modes, then using my stack pointer register, I can implement either ascending or descending stack. Hence, we shall have in ARM all these possible modes of stack operation. We have full ascending, empty ascending, full descending, empty descending. In case of full descending, the stack grows up, but the stack pointer points to the highest address containing a valid item. In case of empty ascending, the stack grows up, but SP points to the first empty location above stack. So, that is why it is empty ascending. Similarly, I can have full descending, whether the stack grows down and SP points to the lowest address containing a valid data. In case of empty descending, the stack grows down and SP points to the first location below the stack. Now, you can realize that if I use stack pointer as my base register with the addressing modes for multiple byte transfer that I have discussed, that is increment after, increment before, decrement after and decrement before, if I use these addressing modes, using these addressing modes, I can implement stack in any of these modes that I have listed. Okay? And this is a flexibility that this ARM architecture provides. If I compare these with a typical processor like your 8085 or 8086, depending on the operations defined for push or pop instructions, the nature or mode of the stack gets defined, and that is defined by the architecture itself. But here the mode of the stack operation is programmer defined. So, we can now talk about stack instructions which can implement full ascending or empty descending. Similarly, I can have the other counterparts as well. So, we talk about instructions LDMFA. LDMFA actually translates to this LDMDA and STMFA translates to STMIB, and SP points to the last item in the stack. When I am using empty descending, this translates to IB, that is increment before, and STMIA is increment after. Okay. And SP used to the first unused location in the stack. Okay. Now, in this case, the interesting feature is, if you look into it, that these are not real instructions. In many cases, the ARM assembler provides these instructions. Okay. And these instructions translates to one of these instruction modes. Next, we have got swap instruction. In case of swap instruction, what happens? A word is swapped between memory and register. In case of SWPB, you swap a byte between memory and register. And this is useful for implementing synchronization primitives like semaphore. If you have already done a course on OS, you know what a semaphore is, and we had also discussed it in the context of PIC, that if we want to prevent access to a common memory location by concurrent threads, that we want to restrict the access to a single thread when a memory location is shared between two concurrent threads, we would like to use semaphores. To implement such operations, swap is a hardware support. Swap instruction is an hardware support. Next, we shall look at control flow instructions. You have got branch instructions, conditional branches, conditional execution. In fact, this is a very interesting feature of ARM. ARM enables execution of each instruction conditionally. Then you have got branch and link instructions as well as subroutine return instructions. And these instructions are all used for controlling your program flow. Typically, branch instruction has got two variants. One is branch, which is actually an unconditional branch or jump. The other one is conditional branch, that is, you branch on a certain condition. In both the cases, you have address label, which is part of the instruction and is a signed PC relative offset. So, you jump to a location whose address is calculated with reference to the current value of PC. Now, we can look at an example how to use this conditional jump instruction. In this case, if you look at here, that we have used multiple multiple byte transfer instructions. This is load and this is store, and then we have compared and then we have jumped. So, I can have R9 pointing to source of data and R10 can point to the start of destination data. R11 in fact R0 and R11 points to end of the source. So, what we are doing here, I am loading this R9, it points to the source of data. So, data is loaded onto these registers and then I am storing them back. So, effectively these two instructions are doing block memory copy. If you look into it, I am copying what? A set of memory locations from one base address, starting from one base address to another base address, because I have got the source in R9 and destination base in R10. So, these are two distinct values. So, I can actually do a block memory copy using just two instructions. In fact, here I am checking whether my R9, that is ends of the source, because whether I have actually reached the end of the source, and if it is not, again I am going back and I am actually doing the loop. So, this is a simple code snippet, okay, of ARM instructions, by which we have shown how these load, store, compare as well as conditional branch can be used. This loop is typically a label, okay, which will be obviously used by that assembler to calculate the address. This address will be replacing this loop, a symbolic reference, and it will be calculated with respect to what? The current value of PC. The assembler will calculate the current value of the PC, and with respect to the PC, the offset will be provided here for doing the actual jump. An unusual feature of ARM instruction set is conditional execution of each and every instruction. We have already shown that I can have branch instruction with condition code, but it is not that you can use condition code only with branch instruction. You can use condition code with other instructions as well. Here is an example where we have shown that this addition, okay. So, this addition instruction is associated with a condition code. Now, what does that mean? That this addition instruction will only be executed when the 0 flag is set to 1. That is exactly the condition code that I am referring to here. Now, if it is not so, what will happen? This addition instruction will be skipped. and next instruction will be executed. So, effectively this add EQ will be converted to a no operation instruction. So, what are the advantages? Why is that in ARM instruction set these kind of instructions have been provided? Obviously, it reduces the number of possible branches. Okay. As a reduced branching, if I am implementing a pipelined architecture, then the number of pipeline flushes reduces. Because if I have a pipelined architecture, then what happens? I need to prefetch the instructions, and when there is a branch, the prefetch instructions have to be removed from the pipeline. Now, when I have a conditional instruction and I am not using branching, then this conditional instruction remains in pipeline, only that this instruction is not really executed, and I replace that by no operation. As a result, since I am reducing the number of pipeline flushes, I have got an improvement in the performance. Also, it increases code density. Why? Because a branch would essentially mean that I have to actually use a branch instruction. If I think in terms of the previous example, I have to use a branch on the condition code, branch on equality, and then I have to use the add instruction. So, the instruction count becomes 2. If I use a conditional instruction, in this case instruction count is 1, and obviously my code density increases. So, a thumb rule says that whenever the conditional sequence is 3 instructions or fewer, it is useful to exploit conditional execution than to use a branch. But if it is really a number of instructions that is to be executed on a particular condition is bigger than these, what will happen? If you use conditional instructions, your pipeline will only have effectively knobs. So, when the condition is not getting satisfied, the pipeline will effectively execute knob. So, your CPU becomes underutilized. Okay. So, when the branching, that is branching, say branched set of instruction is small enough, you should use conditional instructions rather than branch. That would increase code density and at the same time increase efficiency of your code. Next is branch and link instruction. This branch and link instruction is primarily used for subroutine call. So, it performs a branch. Using this instruction you can perform a branch, but along with branching what happens? The address following the branch is saved in the link register. The next value, that is a return address, is saved in the link register. Okay. So, the basic difference between ordinary branch and link is the use of the link register. In case of a branch, the next value of PC is not saved in the link register. In this case, the next value is saved in the link register. So, here we are showing an example, that is when I do a subroutine call, I use branch and link subroutine. So, here I am branching to the beginning of the subroutine, and the return address, which would be the instruction following this branch, will be stored in the link register. Now, I have got only one link register, okay, and there may be nested subroutine calls. What is to be done under that condition? For nested subroutine, you will be pushing R14, that is a link register, and some work registers in the stack, and stack will be set up in the memory. So, here I am just showing you how it is to be done. Say you are now in the first, inside the first subroutine. You have called the first subroutine, okay, using BL sub 1. So, the return address is stored in now link register. So, from this subroutine, okay, from inside this subroutine, you would like to call this. Okay, you would like to call this. So then what you will be doing? I need to save what? I need to save the link register as well as the current working registers. So I use a multiple transfer instruction, okay, multiple store instruction, multiple byte store instruction. So where I am storing? I am storing to the location pointed to by R13, which is my stack pointer. What I am storing? I am storing the work register as well as the link. Okay. So the link register is link of the previous subroutine call. Now when I execute this BL sub 2, the return address from this will be stored in the R14, the current value of R14, and the previous R14 is now saved in the stack. So this is how the nested subroutine call is to be managed in ARM processors. Then how do you return from subroutine? Now there are no specific instructions like return, because the moment I can load my PC with the value of the link register, I have returned to the main flow from where the subroutine was called. So the simplest thing would be this, that is you move R14 to the PC, which is the R15, that is a register which is your program counter. But when the return address has been pushed into the stack, then you can use what? This kind of instruction, okay, a load instruction which uses the stack pointer register R13, and you load the value onto the set of target registers. Now what is interesting in both these cases, you will find that when I am really returning from the subroutine, if I am using these multiple word or multiple byte transfer instructions, what it ensures? It ensures that your registers are always correctly loaded, because these register transfers cannot be interrupted. If I am using, say for example, you do not have these multiple byte or word transfer instructions, or you are not using these instructions, you are using single register transfer instructions for loading the parameters back onto the registers while returning from the subroutine, what can happen? If an interrupt occurs, in between you will jump possibly to an interrupt service routine, okay, and these registers will be lost, and the state of the computation will not be correctly restored when you come back. And in fact, typically when I need to return from this kind of subroutines, I would like to do what? Disable interrupt, so that the status of the registers are correctly saved. Okay. If I am using these multiple data transfer instructions, I make sure that the state of the computation cannot be corrupted by an interrupt. But what is the consequence? I have already told you that interrupt latency increases. So when you are writing a software, this has to be kept in mind, and your timing calculations have to be appropriately done. Next we shall look at software interrupt instruction. A software interrupt instruction causes what we call a software interrupt exception, and this provides a mechanisms for applications to call OS routines. Now typically if you have this instruction that SWI, which is software interrupt instruction, now just like any other ARM instruction, I can have associated with it a condition code, and I have a software interrupt number
associated with it. In fact, in a way you can realize that software interrupt is what? You are actually calling a routine. Okay? That means you are calling a routine which is part of the operating system and not part of your program, that is user code. You are calling a routine which is part of your operating system and not part of your own set of code. Now, what is the basic difference between a software interrupt and a subroutine call? This is the basic difference, that in case of a subroutine, you actually call a subroutine which may be part of your code, and the subroutine can be located anywhere in the memory. But when you are actually using a software interrupt, the software interrupt servicing has to start from fixed locations, fixed vector locations, and that is why you can establish a kind of a universal protocol for accessing OS utilities from the applications of the users. Because if the OS locates the utilities at different memory locations, and if you have to use a subroutine call to do that, then it becomes an unmanageable situation. You have to remember and you have to be notified and told about the location of all these OS routines so that you can use them through a subroutine call. When you are using a software interrupt, the protocol gets fixed. You exactly know where the interrupt handler is located. And there is another real advantage of using software interrupts in case of ARM. There is a mode switch, because I have already told you that your application program will run in user mode, but OS routines will run in supervisor mode. So, when you have to actually call the OS routines, you have to switch mode from user to supervisor mode, and supervisor mode is a privileged mode. So, software interrupt enables the switching of mode as well. In this case, in case of a ARM, it sets a program counter PC to the offset 08 in a vector table. In fact, I am not going into the details, this can be a different address as well. So, as I have already told you, this software interrupt instruction is typically part of user program. So, it is executed in the user mode. An instruction forces the processor mode to become supervisor, and this allows an OS routine to be executed in privileged mode. Each software interrupt instruction has an associated number which is used to represent a particular function call or feature, but this number is not directly used by this instruction. Please keep this in mind, this number is not directly used by this instruction. In fact, what happens is the software interrupt handler routine or the exception handler can use this number for identifying the service to be provided. You need to pass parameters, so use typically registers for passing the parameters. In fact, return value is also passed using registers. So, let us take an example. This is an example of a software interrupt instruction, and in this case you have got, this is your CPSR, which is a program status register. I am showing you these are the flags, condition flags. These are your interrupt enable disable flags, this is thumb mode flag, and this is the mode bits which is now user mode. PC is currently of these values, so currently this is the instruction which is to be executed, and this is a software interrupt instruction. This LR is the link register value, some value, okay, which is not really of concern right now in this context of discussion, and this LR is what? The R14 value, and you can have this register R0, okay. You may use R0 for passing parameters. So, I am just showing some value R0 having 12. So, what happens when the software interrupt instruction is executed? These kind of changes take place. Obviously, the mode now switches to the system. So, it is SVC, and this is what? This is saved program status register. I hope you remember those register that I had talked about in the last class. This is a saved program status register. These register will have the previous value. The previous value, the mode was user, so that is saved. But in this case, you will find that these bits remain unchanged. The other bits remain unchanged. Now, the PC value, okay, has been changed to the desired location, and now this LR is what? This LR value, if you see, LR value will be this location, okay, and what is the interesting feature? The interesting feature here is that your LR is what? Now link register is R14 SVC. R14 SVC is what? The copy of R14 which becomes available in SVC. Okay. Now we shall look at some of the program status register instructions, and there are typically two instructions to control PSR directly. One is MRS, another is MSR. MRS transfers contents of either CPSR or SPSR into a register, and MSR transfers contents of registers to CPSR or SPSR. Now, there are this example. Example is that of enabling IRQ interrupt. So, how will you do it? So, the code uses these two instructions. Okay. This is for accessing CPSR. So, I get the CPSR. Then I use the bit manipulation, the BIC instruction, and then I load it back to CPSR. So, the pre, in this case I was not set, and in this case I was set. So, I am showing in a small the change. So, now this is the modified status of the IRQ flag, that is, this is the masking bit. So, what I have, these instructions are typically executed in SVC mode. So, I have told you that SVC is a privileged mode. So, in that case you can actually modify these bits. Okay. So, that is why you have got these instructions which are available in your privileged mode. In your user mode, you can only change the flag bits and not the status and mode bits. Next, we shall look at coprocessor instructions. In fact, this is again another interesting feature for ARM, because ARM architecture as such is an extensible architecture. That means, what we have discussed so far is basically the instruction set which is supported by the core ARM processor. Now, I can have add-on coprocessors to that core. These coprocessors can be targeted for specific applications. A very common is memory management application. Now, when we have got a coprocessor, what does a coprocessor mean? It effectively means that I am having another processor working with my original processor. And what is interesting, whatever instruction I actually fetch from my program memory, that becomes visible or available in a sense to the coprocessor, and coprocessor can execute those instructions if those instructions are meant for coprocessor. So, that is why in the instruction set of ARM, you have got what are called coprocessor instructions. In fact, the mnemonic for coprocessor instruction is, one of the coprocessor instruction, that is coprocessor data processing instruction, is CDP. Now, this CDP instruction will be useful if and only if there is a coprocessor core present in the actual chip, ARM chip that we are using. And these instructions will have as part of its parts of its operands the specification of the operation that coprocessor is expected to execute. Okay. So, it will be for coprocessor specific instructions. The only thing is that when I have a CDP, so CDP will stand for certain binary code, and by looking at the code, ARM would know that this instruction of the coprocessor, and coprocessor would know this is an instruction for the coprocessor to execute. Now, ARM has a provision for having up to 15 to 16 coprocessors. Okay. So, what you have got as part of the instruction, this field which specifies the coprocessor number. Then you have got opcode. This opcode describes the operation for the coprocessor. That means this opcode is expected to be recognized by the coprocessor and not ARM. And these could be the registers of the coprocessor for doing the operation. In fact, optionally you can specify additional opcode for the target coprocessor. And this is a typical syntax for coprocessor data processing instructions. You have got similarly coprocessor register transfer and memory transfer instructions, because if I have a coprocessor, that is again another processor, it will have registers. I need to have instructions to transfer data between the registers, between register as well as that of memory. Now we look at thumb. Thumb is what? A 16 embedded 16-bit variant of ARM. So what we say in case of thumb, a subset of the 32-bit instruction set is encoded into a 16-bit subspace for thumb. In fact, thumb has a higher performance than ARM on a processor with a 16-bit data bus. What does this mean? It means that if I now build, ARM is basically a 32-bit processor. If I build a processor with a 16-bit data bus, then if I am using a 32-bit processor, I have a degradation in performance. So if I use a 16-bit variant, I shall have a much better performance, because I shall be getting the 16-bit word, and each memory, you can understand very simply, your memory transfer becomes much more efficient. But actually, what have you got? You have got a thumb embedded into a 32-bit processor. So when do you use thumb? Use thumb when you actually require 16-bit operations and not really 32-bit operations. And in many cases, the 16-bit is good enough to specify 16-bit operations, and even 32-bit operations can be also specified by 16-bit instructions. So thumb is good for specifying 16-bit 32-bit operations using 16-bit instructions. So if I am doing that, effectively what happens? My code density increases, and that is the prime motivational factor for enhancing ARM architecture with thumb mode. So thumb is targeted for what we call memory constrained embedded system. Let us take a simple example to understand this code density. This is a code for divide operation. This is ARM code when it is not operating in thumb mode, and this is the code when it is operating in the thumb mode. Now you will find here what I have done is, obviously since it is a subset, the simplest thing is you will not find this kind of conditional instructions in case of thumb, because this cannot be accommodated in a 16-bit instruction word. A 16-bit processor means a 16-bit instruction word. And also you do not have this kind of variance. Subbase is what? The instruction when it affects the flags. Now it is a division operation implemented by, I hope you understand, repeated subtraction. Okay. Now here the number of instructions is 5. Each instruction occupies 4 bytes. So it is 20 bytes is the total memory requirements. Here I am doing the same operation, because if you look into it, I have got I am doing operations involving same registers, okay, R0, R1, and in this case, what is interesting? The total number of bytes required for coding the same division operation is only 12, okay, and this increases effectively my code density. This is the reason why you have got 16-bit thumb mode embedded into ARM. Okay. In this case, I really do not need to use 32-bit instructions. So, I can use 16-bit instructions. The instruction count can be more, but the memory usage is less, and hence I can write code which can be accommodated in less memory. So, typically thumb instructions are subset. So, there are some restrictions. Only low registers R0 to R7 is fully accessible in all operations. Higher registers accessible with only move, add and compare instructions. Only branch instruction can be conditionally executed, that is, I do not use condition code with each and every instructions, and barrel shift operations are separate instructions. We do not provide it as part. Again, the same issue is that of coding the instruction within 16-bit word. And the next interesting thing is, how do you switch from ARM to thumb? So, what we call ARM thumb interworking. In fact, for this purpose, we typically use the instructions BX and BLX. Now, BX is used, this typical syntax is BX R0 and BLX is R0. The BLX is similar to branch and link, and this is a typically branch kind of a thing, branch kind of an instruction. So, when I execute BX or BLX in ARM mode, that I am currently executing in ARM mode, and I execute this instruction, it enters thumb state if bit 0 of the address in Rn, because this register can be any of the registers. Here as an example I have shown R0. So, effectively bit 0 of the address which is specified in Rn is set to binary 1. Okay. So, bit 0 if it is 1 of the address, because this address is what? The branch address. If 1, then this is interpreted as switch to thumb mode. Similar thing true is BLX. If it is 0, sent from thumb, it can enter ARM mode. So, you can see that very easily I can do a switch. Okay. Now, the interesting feature here, you can understand why this bit is used, because if you typically look at it, that an address in case of a thumb mode will have last 2 bits 0 0, because it will be at a 32-bit boundary. Okay. So, that if I am using 1, so I can tell the processor that I am now switching. Now, the architecturally, if you see, the thumb instruction decoder is actually placed in the same instruction data path, what we call instruction pipeline path of the decoder, and this thumb instruction decoder is nothing but actually a thumb instruction decompressor. That means it decompresses the 16-bit compress instruction, okay, to a 32-bit value, which is actually decoded by the actual ARM instruction decoder. Okay. So, now this multiplexer, okay, you have a 32-bit data, and then this multiplexer is enabled by the appropriate bit. If this multiplexer is enabled, then only this decompressor, the instruction will go through the decompressor, and decompressor means what? The thumb instruction is actually translated to a 32-bit instruction internally, so that you can use the same instruction decoder. Is this clear? Externally you are using a 16-bit instruction, internally it is getting decompressed to a 32-bit instruction, so that you can use the same instruction decoder. We shall now briefly look at these architecture 5E extensions. In this case, you have got what? This extension is targeted typically for your signal processing operations. So, you will find in the instruction set of ARM 5E, okay, ARM version 5E, signed multiply accumulate instruction. We have already studied multiply accumulate, but in those cases we said that multiply accumulate does not have a signed version. So, it has got a signed version. It supports saturation arithmetic and it has a greater flexibility in dealing with 16-bit data, so that it can be used for 16-bit audio processing in the ARM mode itself. Okay. So, what is really saturation arithmetic? So, normal ARM arithmetic instructions typically wrap around when there is an overflow of an integer value. I hope you know all that. That is when it is all 1, 32-bit all 1, and if I try to add 1, its value will become 0. The similar thing, if there is an underflow beyond 0, 0, it will become all 1s. So, that is basically the underflow and overflow wraparounds. Now, using ARM v5e instructions, you can saturate the result. That means the result will be stuck at the maximum or the minimum value. So, the result remains at maximum or minimum value. Okay. So, this is saturation arithmetic, and for that you have got additional instructions. These instructions typically are indicated by Q as the first letter. I have given two examples, Q add and Q sub. So, in this case overflow or underflow will keep the value of the corresponding result register at maximum or minimum. So, this finishes our discussions on ARM instruction set. We have also looked at today thumb mode of ARM and the other aspects of this ARM architecture. In particular, we have not discussed in detail interrupt processing, because you know interrupt processing is critical for any embedded applications, as well as other features of ARM architecture we shall take up next. Any questions?
So, what is the motivation for the fourth stack that we saw?
See, it's the question is, what is the motivation for different mode of stack operations? This different mode of stack operations is decided by the programmer. What I have tried to illustrate is that these different addressing modes facilitate stack implementations in all these variants. It is not architecture defined. So, this the flexibility that these different addressing modes provide you, that enables a programmer to implement stack in any of these modes that suits his application. Any other question? Okay, then we shall meet in the next class and discuss remaining aspects of ARM architecture.